So yeah, so in IIT we have this idea that the cause-effect structure is in one-to-one correspondence with it doesn't directly address how things from the outside world enter our experience, right? So that's one of the questions we want to address with this framework. And another one is just, what does IIT have to say about meaning? Mean for a stimulus to be perceived by IIT? And then how does the structure of experience match causal processes in the environment? Because there's obviously some kind of relationship between the structure of our experience and what is out there in the world. And I should mention that this work on matching was enabled by background conditions in a sense. So this actually goes back at least 30 years to a paper that Julio had with Olaf Sporns and Gerald Edelman, where they developed a complexity measure that they used to address some of these questions in that framework. And so what I'm presenting now is basically the formalism updated to work with IIT 4.0. So the setting here is, it's a pretty familiar approach by now, probably. We just want to show that these ideas work. We have a proof of principle in a very small model, because that's where we can actually calculate the exact quantities. And so we have an environment, which is just, conceptualized as a bunch of elements that are in some state. They impinge on a system through a sensory interface. And that is the connection from the outside world to the system. And the system is going to be sort of a multi-layer neural network, essentially. And I won't get into the details of that neural network. And Björn was kind of the one who was focused on building that, actually. But it essentially has these 3 levels. So the level 1 is essentially, sort of like the retina, or like V1 maybe, where it just faithfully reproduces what is on the sensory interface. Level 2 contains what we call configuration detectors, and their role is to activate in the presence of certain configurations in their receptive field. So for example, when you have off, on, off, that's something like a segment in the middle of its receptive field, and that will cause this unit to activate. And then on the 3rd level, there is an invariant detector. And the role of that unit is simply to say, okay, one of these configuration detectors is on, which means that somewhere on the sensory interface, there was this pattern that those configuration detectors are selected for. Okay? Yeah.
The reason why sensory interface and level 1 are 2 separate things is because that level 1 is connected with way what the sensory.
Yeah, exactly. The sensory interface is just feed forward. It's just impinging on the system. And then, we're basically in this work, because it's the calculations are so difficult, we sort of assume that all of these are part of the main complex. Yeah. So we're not actually dealing with that question here. But yeah, in this model, there's feedback connections. So level 1 can be part of the main complex for that reason. Yeah.
So in a way, that's very important. So in a way, this system.
Yeah, that's right. Yeah, I mean, I'll get to this in the very end, but we're not considering the motor side at all. There's no feedback from the system to the environment here. Yeah, exactly. They may be, other conscious entities, other people, or, whatever. We're not really specifying that. So from the perspective of the system, this is really, we're just talking about this sensory interface as having some statistics that we're interested in, right? Yeah, sensory interface. Okay. Well, I guess it's an interface, so it's between. That was the idea. But sensory sheet is another term that was used in the 96 paper, whatever you want to call it. Yeah, the point is it's outside of the system. Yeah. Any other questions? Okay, so yeah, so this is the basic idea of the model system that we're working with. We have 2 versions of this system. So one we call a segment detector, because the configuration units are set up to selectively activate. I mean, they're all probabilistic, but they activate strongly in the presence of these patterns where there are 3 in the middle that are on, or 2 on one side, or 2 on the other side. So there are 3 patterns that they activate, and they sort of look like segments. Then there's the centered odd detector is a system where the configuration detectors actually work so that they also activate in response to these 3 in the middle, but they also activate in response to just one in the middle. So whenever the pattern is like an odd number of on units and it's in the center, that's when they activate. Otherwise, they're exactly the same. And that's shown here. So these are the patterns that they're selected for. And then the invariant detector will sort of activate whenever any one of these patterns is present on the sensory interface. And then this is just kind of showing the activity. You know, we ran some simulations and just showed like, okay, so this is the input pattern on the sensory interface. And then level 1 is just faithfully reproducing that pattern. And then when there is a segment pattern, you see that the configuration detectors activate, and then the level 3 invariant unit activates. And the same thing for the centered odd detector. Yeah. Question, sorry. Yeah. I will get into that later, but basically it's to illustrate some conceptual points. Yeah. Yeah, it's just to have systems that are sensitive to different kinds of patterns so that we can use them later to illustrate some points, which I'll show. Any other questions? Okay. So, all right. So the first thing to say, I guess, is that according to IIT, the cause effect structure is in one-to-one correspondence with the experience, right? And so one of the implications of this is that meaning, whatever that may be, must be intrinsic to the system. It must be contained in the experience, which in IIT is the cause effect structure. And this is kind of a simple point, but it's pretty deep, I think. And I think you can kind of see where that comes from when you consider the case of dreaming, right? So if you're disconnected from the environment, we all know that when you go to sleep and you have a vivid dream, you're still having sort of a meaningful experience. And yet, because you're disconnected, there's no sense in which that meaning of the experience can derive from some connection to the external world, okay? And so in the model, we sort of model this by just disconnecting the sensory interface from the system. And then we can unfold the cause effect structure that is specified by the system in this state. Here, it's all off. And we still get a very rich cause effect structure. So, you know, presumably the system is having some rich experience despite not being connected to the environment. Now, you're going to see a lot of these plots. It's not so important, actually, what they say. They're very hard to read, but basically, these are the mechanisms, and these are the causes, and these are the effects, and the lines are relations between them, and their color is the phi value. And yeah, so that's kind of the first point, is that in IIT, meaning is intrinsic, and this is sort of summarized by the slogan, the meaning is the feeling, okay? Yeah.
One thing is that experiences like bringing our because even thinking of your mind, but even this relation.
That's true. Yeah, it's not that all dreams are like this. It's just that in the general case, you know, when you're disconnected, you can have an experience, right? So, I mean, as far as I'm aware, it's not true that like every dream is like that, right? Yeah, and this is a point that comes up a lot when I talk about this, but that's true. And indeed, of course, our experiences are shaped by our like history and, you know, evolution, development, learning and everything. And I'll get into that a little bit later. But the point is that it isn't necessary, right? So that's a contingent fact. But according to IIT, at least, if you're having an experience, it's a function of the state and the causal powers of the system, and that alone. Now, it turns out that in our case, of course, we're well adapted to the world. We have the ability to perceive structure in the world. So our experience does relate to the world in that way, but it isn't a necessary part.
It's true, but also it's true that there isn't that much difference. You've got the sum of it, the face and the system. Sort of a change, but the projection of the yeah.
Yeah, I guess so. Not sure I fully understand your point, actually, but okay. So yeah, and then we consider the case, of course, where now we connect the system to the environment. And this is kind of like the awake condition. And And this is analogous to, when you're awake, you're looking at a stimulus, and of course, we can still unfold the phi structure. But in this case, what is in the phi structure is going to be affected by the stimulus, right? And so this is kind of the case that we want to consider related to perception. And so to give an account of perception here, the key idea is that we want to consider a component of experience, a percept, to the extent that it was caused by a stimulus, right? So we have, the dreaming case where nothing is caused by a stimulus, it's all sort of intrinsic. And then in the case of perception, there's a stimulus, and there are going to be some parts of the experience that are caused by that stimulus, and those are the ones that we should consider to be percepts. Mm-hmm.
In the case of the dream, it's connection of the dream to the data is local data.
Yeah.
So that means that function.
Yeah. Yeah.
Well, everything else, make the first data zero. So the most strong each of the individuals or equal.
Yeah, I think that's a good point. It's a bit of a technicality here, but yes, and I think maybe we can discuss after. Yeah. But in general, it's true. Okay, so then if that's what we're going to define a percept to be, then we have to answer the question, how do we assess the causal role of the stimulus? And so to do this, we're going to draw on Larissa Albantakis's work on actual causation, which is where she sort of adapts the machinery of IIT to answer the question, what caused what? And so to do that, there's not going to be too much math in this talk, but basically we're just interested in two probabilities. One is the conditional probability, the marginal probability. So the probability that the mechanism that we're interested in is in a particular state, given that the sensory interface as a whole was in some state, that's the stimulus. So the probability of a mechanism state given the stimulus versus just the probability of the mechanism state after marginalizing out the stimulus is just its generic tendency to enter that state. So those are the two probabilities, and we simply take the log ratio of those probabilities, and we define that as connectedness. And this is basically a measure of the extent to which the stimulus was responsible for causing the mechanism state, right? So it has some, marginal tendency to enter that state, and then when you have the stimulus there, that might raise the probability, might lower it. So that's our measure of connectedness. And so that's high when the stimulus raises the probability of the subset state relative to its average tendency to enter that state. And it's maximized when the stimulus deterministically causes that subset state. And if you know some information theory, you might recognize this as actually the positive pointwise mutual information. So this is a very common measure that already exists. But in this case, where we're considering, the stimulus occurred before the mechanism state, then it's kind of a causal measure. That's the idea. Okay, so that's connectedness. And connectedness depends on the size of the subset. Larger subsets can specify more bits, basically. And since in IIT, the distinctions, it doesn't really matter how many units are specifying those distinctions. Each one contributes to experience as a quale. We want to deal with the subset size by normalizing it. And so we introduce this term that we call the triggering coefficient, which is just simply the connectedness normalized by the maximum possible value of the connectedness for that subset. And that brings this in the range 0 to 1. And so when it's 0, that happens when the subset state never occurs in response to the stimulus, and then it's 1 when it always occurs deterministically. Okay? And so when we measure this for our little model system, the segment detector, I'm not showing the level 1 values because there's too many, but we can see that for the invariant detector, when it's on in response to a segment here, we see that there's a relatively high connectedness value, and then correspondingly a high triggering coefficient. And that's because the invariant detector is quite selective, right? It doesn't turn on for most stimuli. It only really turns on for the ones that activate it, which are the segments. And then likewise for level 2, you can see that this configuration detector is on. It's detecting this segment here on the layer 1. And for those subsets of the system in level 2, where it includes this selectively on unit, then it has a high triggering coefficient. Okay, so that's kind of what this is showing. Any questions for now? All right, so that's the triggering coefficient. So it's not really that complicated, but it provides a nice way to kind of get at the question of, for a given subset within a system, how much did the stimulus cause that? Melanie? Sorry, I can't hear. Yes, yeah, exactly. Yeah, if it's all deterministic and every time the stimulus activates that, and that's the only stimulus that activates that, then that'll be 1. If there are other stimuli that activate it, then it might be less than 1. And also if it's indeterministic, it maybe will be less than 1. Yeah. Okay, so
I should remember this question. Sorry. Why did you? What's the mission?
yeah, so that's like I was saying, yeah, they're very much getting at the same idea. It's just that connectedness is dependent on the size of the subset. And so triggering coefficient is basically just a normalized form that deals with that.
Why do you want to know?
Because you want to compare different distinctions and relations, as I'll show in the next slide, on the same basis, right? Because they sort of, there's no sense in which one is privileged, one distinction is privileged over another. They all equally sort of contribute to the qualia, right?
So the second one is just normalizing first.
Yeah, exactly. So that they can all kind of be compared. Okay. So then, armed with the triggering coefficient, now we can kind of define this thing that we call the perception value. And this is simply the product. We're just weighting the phi value of a given distinction or relation by its triggering coefficient. And that's what we call the perception value, okay? And so this is essentially the fraction of the phi value that can be attributed to the stimulus. That's the idea. And while we were developing all of this, we actually noticed that there's a kind of nice decomposition of the big phi value, which is the sum of the small phi values for all the distinctions and relations, into what we call phi-folds. And so each subset of the system specifies one of these, and I'm plotting them all here. And the idea is that, so you have a particular mechanism that's one of the subsets, and then it has its effect, has its cause, and these are related to all the causes and effects in the rest of the cause-effect structure. And basically, we can consider this to be the part of the cause-effect structure that's specified by this. So we're kind of including the relations in that and weighting them by how many other distinctions are related to them. Yeah.
This is a different visualization of the structure.
Yeah, this is different. Yeah, it's. Yeah, exactly. I'm only plotting the second order relation. It's quite hard to visualize with the system of this size. So we kind of needed a larger system to illustrate some of the points, but when you get that big, it becomes really difficult. So we never really found a good one. This one's obviously pretty hard to see. Yeah. Mm.
This one, which is probably different from the I think.
Mm-hmm.
This is back so it's basically whatever experience is there. This concept is called perception.
Right. Right.
Which that color, I mean, is it picture? Because I'm expecting to be a little part in groups. I mean, the fraction, as you can say, is not derived the stimulus.
Yeah, I mean, that's an empirical question ultimately, but I mean, just thinking about my experience, I would expect it actually to be quite high in some cases, right? Especially for like low-level percepts, like just a field of color in my visual field. I mean, that seems to be directly caused and exclusively caused by something that's out there, by some reflectance, right, off a surface or something. Yeah. Mm-hmm. But to illustrate that point, I mean, it's a good point, right? I think like if you're talking about maybe a higher level thing where you're seeing a color and that reminds you of your grandmother and some experience you had or whatever, those would be less caused, right? Those quali.
I'm not just seeing a circle, a colored circle. It's required me to try to putting them together. So circle, there is this color.
Mhm.
I mean, which part is actually, because by this one part, which needs to be tried.
Yeah, I mean, in those cases, I think we don't make the distinction, right? The memory retrieval, that is in itself a quali as well. And if it's triggered by seeing a circle, then, then you do this calculation, you see it's caused by that, and then we would say it's a percept in that sense. Yeah. Yeah, I mean, in a way, it's a bit agnostic, right? It's not really claiming that there's some division, and this is indeed different than like typical cognitive science, right? We're not saying there's some division between memory, attention, and perception. It's just saying you have an experience. It is composed of all these different elements, and attention and memory and all of those things are part of it. And you're just interested in, when I see something, when there's a stimulus, to what extent did that selectively cause all of the stuff that I'm experiencing now? So it can be unconscious? No, in that case, no, because I mean, just sort of technically, we're multiplying the triggering coefficient by the phi value, right? If it has a phi value that's non-zero, then it's part of the cause effect structure and is therefore, according to IIT, conscious. So if there's something that doesn't have a phi value, or it's not even part of the main complex, it's some unconscious, subcortical region or something that's responsible for some function, but it's not in the cause effect structure, then there's nothing that you can even multiply it with. So it's zero, it doesn't appear.
The inner inside of this consciousness, what is positive? So in this operation, there's no conscious perception.
Yeah, exactly. By definition, almost, it's saying, perception has to be conscious. Yeah. And you can talk about unconscious perception, but then it's something else. Yeah. Yeah.
Is there a experience to that?
What do you mean exactly?
To actually change it.
Uh, well, I mean, in this framework, we're just talking about the sensory sheet, right? I mean, I guess if you're like doing TMS or something, you can perturb it within the system too, but we're not really considering that case. I'm not sure I understand, but
Sure, what do you like? This is really what I said. So if you probably change the connection of the system, say especially for the feedback, second or first layer, then that's only small.
yeah, I suppose. Yeah. 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 If there's a lot of feedback driving the thing, then I guess, yeah, it would go down, right? It's less triggered. Sure. Yeah.
Yeah. So you see.
Yeah.
So perception. Usually it's different accent.
Explain the training. We assume that connection from the environment. It's because there are a lot of connections.
Yes.
Mhm. Yeah.
Yeah, so let's say
Yeah, it's good to discuss it. But okay. So yeah, so once we can decompose these the cause effect structure into the five folds, then we can we can consider the cause effect structure as a whole again. We got to have freshly mowed grass. That's good. But yeah, so we can consider the whole cause effect structure again, and now we are weighting each fivefold, which again, this is a decomposition. So when you put them all back together, you recover the whole thing. And we're weighting each one of these by the triggering coefficient for the mechanism, for the subset, right? And the result is that we have kind of a version of the cause effect structure where everything is weighted by how much the stimulus caused that part of it. And then we can sum up all the perception values for all the fivefolds, and then we get some fraction of the big five value. Okay, so it's just kind of a neat decomposition, and this gives us a sense of, to what extent was the entire experience perceived in the sense of being caused by the stimulus. Yeah.
These things from class structure, same as well.
No, not exactly. So I didn't explain that super well, but basically there's a one-to-one correspondence between fivefolds and distinctions, right? So the distinction is kind of at the base in a sense, but it also includes the relations between the cause and effect and the rest of the causes and effects as well. So it's essentially a way of, now that we have relations, we have to find a way to fit those into the decomposition, and that's what it's doing. Yeah. Okay. Okay, so then we can extend this idea. So for a given cause-effect structure, we have a perception value that sums up the perception values of the fivefolds. And now we can consider a sequence of stimuli, right? So we want to treat now, instead of just one stimulus causing an experience, we have a sequence that causes a sequence of experiences. And so in this case, we have the segment detector that's being exposed to a world, an environment where there are segments. So this is conceptualized here as just a bunch of sort of random noise, and then there are these two causal processes in the environment which have a tendency to generate segments and impinge on the system through the sensory interface. So there's one that generates 3 segments, there's one that generates 2 segments. And in this case, it's perceiving a 2 segment, and this, we unfold this into a phi structure, then we do this thing I just described with the perceptual structure. And then as time goes by, there are more different stimuli. This is a 3 segment, and now another 2 segment in a different location. And so we have this set of phi structures that corresponds to this sequence of stimuli, and then we have the perceptual structures. And then the idea is that we just take the union of all of these perceptual structures, and we combine them all into one larger structure, which we call a differentiation structure. And then we can sum up the perception values, just as we did before, for this sequence. And this kind of represents, essentially, if all the stimuli are the same, then they're not going to be triggering different concepts or different distinctions, right? And so this is a means of capturing the extent to which not only does a stimulus trigger a rich set of highly connected quale, it's actually also, triggering different ones, right? So you're having a rich and varied experience over the course of a sequence of stimuli. Does that kind of make sense? Any questions? Yeah, Alex. I'm not sure. Yeah, I'm not sure if that, I don't know if I understand what you mean there. Yeah. Yeah, but we're not subtracting. I mean, we're taking the union, right? So
Here's a union does distinguish the. So that's why you get the discounting the over.
yeah.
Discounting over then color is what.
Okay. Yeah. Well, in that sense, then yes. Yeah. Right. Yeah. We're just saying, yeah, we don't count them multiply. It's that simple. Yeah. Okay. So that's this quantity that we call perceptual differentiation. Okay, so now that's kind of like the first part of the formalism that I just explained. In a way, it's quite simple. And then we can use this to kind of examine some implications of IIT. And so one is this idea of perception as interpretation, okay? And so in this example, we're going to show the same stimulus to these two different systems, which detect different kinds of stimuli. So this is an environment where it generates centered odds. So there are these causal processes that tend to generate, this one generates a single point somewhere on the sensory interface, and this one generates a 3-segment, okay? And let's suppose that we have a single point on the sensory interface as the particular stimulus that we're sampling from this environment, and we present it to the segment detector. Okay, so the segment detector only detects 3 segments and 2 segments, right? So this stimulus is not going to activate the configuration detector in level 2. And we can unfold the phi structure there, and then we can calculate the perceptual structure, and we can calculate the perceptual richness, the sum of all the perception values. And it turns out to be this value. And we can do the same thing for the centered odd detector, okay? And in this case, the centered odd detector by design is selective for this stimulus. So this stimulus will percolate over, 3 time steps up to the top level. It'll activate this configuration detector and the invariant detector. And then we'll get another cause-effect structure corresponding to this experience. And it turns out that this perceptual richness value is going to be higher. And technically that's because these units are selective. So they have more cause-effect power in that sense when they're on. And so the idea is that, we have the same stimulus, but we have different experiences. And so this centered odd detector is interpreting this stimulus through its intrinsic connectivity, the way that its units are designed and their cause-effect power, to be sort of more meaningful in a sense, right? So this stimulus for this system elicits kind of a bigger, more rich cause-effect structure. And so in that sense, perception is interpretation. That's the idea. And we can actually take this further and we can say, okay, well, what if we present a segment that comes from this segment environment? And it, by the design of the system, they're both actually sensitive to 3 segments, because a 3-segment for the segment detector is one of the 3 segments that it's sensitive to. And for the centered odd detector, a 3-segment is also a centered odd. So this centered odd detector will also activate in response to this stimulus. And in fact, the activity pattern that you see, the activation, will be exactly the same for the both systems, right? So they're both selective to this stimulus. We do the same thing, but of course we get a different cause-effect structure, right? Because the units, the configuration detectors in particular, are set up differently in each case, right? And so the idea here is that it's not that the meaning is in the activity pattern, right? The activity pattern as such has no meaning, because the only difference between these two are the counterfactual, propensities for these units to respond differently to different stimuli, okay? So that's kind of a very important idea in IIT, is that it's the cause-effect power that matters, right? Not the activity. And I think that's kind of, illustrated nicely by this example. Right. Right. Alex?
Either the connectivity or so if I look at
Yeah, in this case, the only difference is the function that this unit is implementing. Well, this unit is selective for different sets of stimuli than this unit. So yeah, it's not illustrated here, sorry, but yeah. Exactly. Yeah, and so even though the activity pattern is exactly the same, the connectivity is exactly the same, the causal powers are not the same. Yeah.
slide, how are you still getting conceptual richness?
That's a good question, but it's just kind of a contingency of the models that we're working with. It's like these models like to dream or something. I don't know. I mean, but hopefully it's enough to illustrate the point. Yeah. same question. Yeah, okay. Yeah, so I mean, the actual values here are just not so important. The point is to show that they're different, right? So each system is interpreting the stimulus in a different way. They're both perceived, but they're interpreted differently. Okay, so that's one point. So that's the slogan, perception as interpretation. And then another point is that, you know, like I said at the beginning, in IIT, meaning is intrinsic. And in particular, this means that it does not require reference or any notion of representation, okay? And so the idea here is now we just stick with one system. We have the segment detector, but we have three different environments that we're exposing it to. So we have the segment environment, which I already described, and then we have a modification of that environment where instead of having a 3-segment generator, there are simply two 2-segment generators, okay? And so let's say that from the first environment, we have a 3-segment right here. And it's possible that in the second environment, we could have the two 2-segment generators overlapping. They both sort of send their 2-segment to the input array or the sensory interface such that they overlap on this middle one. And the overall effect is that the state of the sensory interface is the same as in this case where it was just a 3-segment that was being sent there, okay? And likewise, if we consider a third environment that's just pure noise, it's of course possible probabilistically that we end up with a 3-segment by chance, right? And so the idea is that in all 3 cases, now the phi structure is going to be exactly the same because the stimulus is exactly the same. And so will the perceptual structure and the perceptual richness, right? And so the idea is that, you know, in some accounts of meaning, you know, you need some notion of reference to an extrinsic thing to ground the meaning of the experience or the thought or whatever. But this is kind of illustrating that according to IIT, you know, in this case, there's literally nothing out there that could be a reference, right? So the interpretation of this stimulus by this system, that meaning of that can't be grounded anywhere because there's actually nothing out there by construction in this example, right? And indeed, like even in the cases where there are things out there, you know, you don't know what it is necessarily, right? So that's hopefully illustrating that the meaning has to be sort of without any regard to reference or representation. So I don't know if that was clear, but Reina. No, this would be like in the environment. Like if you were placed in like a pure, you know, white noise, like to take the case of vision. Yeah. Yeah, well, so yeah, and indeed it's a probabilistic system. So like I'm always sort of illustrating the case that I want, but in fact, when you present this, it might not actually activate. And then you would experience something different, right? You like, in a sense, wouldn't see the stimulus properly or something like that. But in each case, it has a phi structure. So I hope maybe that answers your question. I'm not sure. We can talk after. Right, yeah. Yeah. Yeah, exactly. Yeah. Thanks. Yeah.
These 3 cases, it's still something out. It's just the same thing. A different things could be the same. So I could see the representation of this there's something there. But at least you're breaking the function for what's the line.
Yeah, I mean, yeah, there's probably some responses along those lines, but I think that the case of noise is particularly difficult to respond to, right? There's no structure at all. You're supposing that the world, you know. Yeah, but then are you saying that the meaning of that is grounded in what, right? In the state of the sensory interface? I mean, it seems a bit weak, especially considering that, like, you know, I mean, take the example of like I'm in a pure noise world and it just by complete chance, this particular scene that's here right now that I'm seeing happens to appear by chance. I would have the same experience that I'm having right now, a very meaningful experience. I recognize all of you, I'm talking, blah, blah, blah. but there's nothing actually corresponding to that in the real world by construction, right? So that's the thought experiment, kind of. Yeah, like Anastasia presented to us yesterday, I think. Yeah.
Yeah. Representation is not over.
Mhm. Different meanings. Yeah, I mean, that's a good thing maybe to bring up in the discussions this afternoon, but in a way, we're kind of co-opting the term and sort of asserting that like what it should mean is experience in a sense. But yeah, there's obviously different meanings. Okay, yeah, I think this should be okay. Okay, so that's kind of our attempt to formalize this extension to answer these questions. And now I'm going to talk briefly about this aspect of the work. How does the structure of experience match causal processes in the environment? Okay, so this is like the last kind of technical part where we define this quantity called matching. And the idea is that we're going to try to measure the perception that's attributed to causal processes in the environment. Rather than just stimuli on the sensory interface, we're now interested in what is actually like out there. And so, this is what I already showed. We have the differentiation value of this union structure. And this is when the system is connected to the environment, okay? So we have stimuli being generated by an environment. We can also consider, yeah. Yeah, well, it's just kind of like what I was showing in the previous figure, right? So you can have a noise world where there's just independent noise sources. There's no causal structure. And then by chance, you can have a stimulus that happens to be very meaningful for the system appear on the sensory interface. But if you were to go out into the world and start perturbing things, you would discover that actually it's just randomness. There's no structure. So that was a totally chance occurrence. Whereas instead, in this world, I can go out and I can like see that, oh, the reason I'm seeing this thing is because there's something here I can perturb and observe. Okay. And so the idea is that we can leverage this notion of a noise environment, and we can expose the system that we're interested in to a noise environment where there are no causal connections and there's nothing there. And so this is kind of just like what you were saying now, where we're just looking at white noise forever. And then we can measure the differentiation that occurs in response to that, okay? And the idea is really quite simple. We just take the difference between those two, okay? So you expose a system to a world. The world generates a bunch of stimuli. Those stimuli are more or less meaningful to the system as measured by this formalism. Then you take a world which has no structure and you do the same thing. And then the difference will kind of isolate the portion of that differentiation or that meaning that is due to the causal structure of the world that you removed in the noise case. So it's kind of like a control condition, okay?
Because you're thinking you're doing it, within the second.
Yes, yeah, that's a very good point. And we do deal with that in the paper. It's a bit technical, but there is kind of a way around that, having to do with contiguous subsequences, and we take the maximum. So there's a section in the paper, but I think I probably don't have time to go into that, but we can deal with that problem. Okay, so now here's just a brief example of this. And so this is a segment environment. This is the uniform noise environment, which has no structure. We take samples from each of these environments. In this case, it's 4 samples, and we're doing 32 trials. And then we can present those to the system, and we look at the perception value for each of those. And in this top 2, this is the segment detector system being exposed to the segment environment. And then we can basically take the average difference between the environmental perception value and the noise perception value. And that difference is plotted here. And then we do the same thing for the centered odd detector. Now, the centered odd detector is not really designed to respond to the 2 segments. And so overall, when we do this calculation, we see that there is less perceptual differentiation in response to that world. And so in this sense, this is kind of a concrete example showing how the segment detector matches better to the segment environment, which is what we would expect. And then vice versa, you can do the same thing where you present both systems with the centered odd environment, and the centered odd detector now matches better. Okay. Any questions on that? Yeah.
Is this an empirical measurement that you're taking, exposing it to setting universe?
Yes. Yeah, exactly. I mean, empirical, it's all in silico, but no, we're just randomly sampling 4, and then we do 32 trials of that. Yeah. Just to kind of illustrate how this would work in an experiment. That's another detail. There's basically 5 time steps that elapse to allow the stimulus to percolate through. But I think I don't have time to describe that in more detail, but we can talk after. Okay, so just to recap quickly, so connectedness and the triggering coefficient, those measure the degree to which a stimulus specifically causes the state of a mechanism within the system. The perception value measures the degree to which an intrinsic meaning was triggered by a stimulus. That's just this multiplication. And then perceptual differentiation is the perception value of the union of the cause-effect structures that were triggered by a sequence of stimuli. And then finally, matching is the expected difference between the perceptual differentiation triggered by the environment versus noise. Okay. Okay, so then I'll just talk a little bit about, what matching is doing. So in essence, matching is capturing how the system's connectivity has internalized environmental regularities. So in the case of the segment detectors, by construction, we had them internalize the regularities of the 3 and the 2 segments, okay? And so in general, perceptual differentiation will be high if the environmental stimuli percolate broadly, deeply, and strongly over all the subsets of the system, as the segments do in the case of the segment detector. And if those subsets specify 5-folds of high phi, right? So the stimuli have to trigger many different distinctions and relations that have high perceptual richness. And then because of the union operation, they also have to trigger different distinctions and relations. And then matching will be high when the environmental stimuli, but not random stimuli, do that, right? When they elicit high perceptual differentiation. Matching will be 0 if the system is not a substrate of experience. And then there's no consciousness at all, so there can't be perception. If the environment has no causal structure, then on average, if you do that experiment, they'll converge to 0. Because the difference will always make it 0. And then if the system's not even connected to the environment, then of course matching will be 0 as well, right? And so the idea is that matching should be increased through evolution, development, and learning. These are the mechanisms by which the intrinsic connectivity and the causal powers of the system start to internalize regularities in the environment, right? And so well-adapted brains, like ours, should allocate intrinsic meanings preferentially to the interpretation of important causal features of the environment, which is why our visual system sort of like works to see, right? So that's kind of the take-home message for matching right there. Yeah. Yes, sure. Yeah, and that reflects the brain's ability to go beyond the information given. And then I won't talk about this. This is an empirical application of this idea, but I don't have time. And then just some future directions. We want to extend it to the output side, which I didn't talk about at all, though some questions came up on that. And then this is something that has come up a few times, actually, in the past few days. We want to develop a more principled way of comparing and aligning and taking the union of these cause-effect structures. And that has some implications, I think, for the quality of structure program in general. And then this is, I like to get on my soapbox and just complain that we don't have any proven tractable approximations to phi, and that's clearly necessary to actually measure this in practice. And then you could analyze the whole football team. Okay, thanks. Sounds good. Yes, that's the substrate modeler thing. Thanks, Francesca. Yeah. So the substrate modeler is like Björn's, it's on GitHub, it's public, and it's what he used to make these systems that we analyze.
the Pi-Fi boards.
No, no, and
You repose it.
it's on Bjorn's
Bjorn's.
account. I can send it to you.